Wait,
yeah, no, not in this room. There's like tables right outside. Sound good with you, or?
Yeah, that's cool. I mean, as long as like someone there.
Hi everyone.
Is it like tutor?
Well, you can go to the tutor place, but then you can always ask tutor for help.
Yeah, but I feel like you know, something like simple, you know.
So the plan of today is I prepared some questions from some people sent me questions by email, some emailed me just general requests like do such and such type of problem. So I try to do respond to these kind of requests. Then maybe we'll have about 15 minutes to discuss any questions that you wrote just here. Maybe let me start with just, do you have any questions in general about the final exam, how it looks like, or I don't know, any kind of questions? It is out of 100, yes. How many? Please look at the previous exams for guidance. I mean, it has the same structure, many short answer questions and a couple of long questions. So the structure is pretty close to what it used to be. And yes, a good idea for preparation would be, well, do try to solve the previous year's exams. We did not cover some of the topics that were included in past years. We did not cover, say, L'Hopital's rule. We did not cover inventory. We did not cover, well, yes. So we did not cover, say, error term in higher order Taylor estimation. We did not cover. Well, so there are several topics that we did not cover and were tested last year. So just skip those and try to solve those the problems that you can solve. I mean, if you encounter some not familiar words, then most likely it's. Yes, we also didn't cover Newton Raphson method, so these are the major topics. So try to solve the previous exams from previous years. There are solutions to the last two exams from 2010 to 2011, and 3 exams without solutions. If you run out of those questions and you have spare time, you can try to review the web works, then you can try to review the suggested problems. So there's lots of material to review if you have time. Yeah?
Are there questions on the final exam that we haven't reviewed in class or discussed?
So, I mean, there definitely will be questions not exactly the same as we discussed in lectures. I mean, it should be expected. We cannot cover exactly the same kind of questions, but definitely they will all be on topics that we did discuss in class. So, I mean, pretty much like in midterm. The questions might be slightly different from what we did here, and slightly different from the web works, and slightly different from suggested problems, but still, I mean, on the same topic. About the level of difficulty of final, so there will be, I mean, I can't tell you in general whether it's easy or difficult, but there will be questions which are quite easy, I would say almost immediate. Some questions will be, well, a little bit tougher and a little bit trickier. So if you get to some question, and they are not in kind of order of increasing difficulty, they are mixed. So if you encounter kind of early on a question that is difficult, it's better for you to skip it in the beginning, try to do some other questions, and then return to it once you have time. So it might be a good strategy to do as much as you can on the easy questions, and then try to do the harder ones. So maybe any other questions? Okay, so I guess I'm also not really allowed to say much more about the exam. So several people have asked me to discuss some optimization problems, so we'll start with one of those. Copies, 10 hours. Me. A and type if in a copy spends 3 hours looking for A, gets 4t squared minus 3 cubed by 3 pounds of A. So I'm looking for B. And copy gets 2 pounds of B per hour. If the nutritional value of B is 3.5 times larger than that of A, how much time should the copy spend looking for A to maximize the total nutritional value? Looking for A to maximize the total nutritional value. So let me read this question aloud. We have so some animals, a puppies, it's given that they spend every day 10 hours looking for food, and there are 2 types of food, and it can gather either one of those or another one, but not both of them simultaneously at the same time. So what's given is if it spends t hours looking for the first type of food, it will get so many pounds of this food. If it spends, well, for every hour which it spends on looking for food of type B, it will get 2 pounds of B. It's also known that the food of type B is more nutritious than food of type A. It is 3.5 times more nutritious. And the question is, what is the best strategy for a copy? How should it get the most, how would it be able to get the most nutritional value during one day? And I must admit that, well, first of all, I've taken this question from exam in a different course, but it is quite suitable for this course as well. Second thing, I've never seen an copy except yesterday in Wikipedia. But, well, I guess it's all quite irrelevant to the question. So let's discuss the question itself. First of all, this is an optimization problem. We want to maximize something, some quantity. And we are given that we can change some parameters, namely the strategy of the copy, how many hours to spend for one type of food and for another one. So let's discuss first of all the objective function, what we are trying to maximize. So what would it be? Well, that's always the easy step in any optimization problem. It's just look for the word maximize or minimizing the problem, and whatever follows is the objective function. So here, to maximize the total nutritional value, so our function is the total nutritional value. Let's say B is the total nutritional value. The good idea at this point is, well, not to think exactly how we will express it in terms of the parameters, just what is the function. Then think separately about what are the parameters. And for this we actually have some hints in the problem. So the parameters are those things which we are allowed to change. In this case it would be, well, we are allowed to tell the Akapi to look so many hours for food of type A and so many hours for food of type B. And that's basically all the freedom that we have. We can't influence the nutritional value of B, we can't influence more or less anything else. So let's say there are two parameters which are important. One of them is actually given a name in this problem. If an Akapi spends T hours looking for A, so T is the number of hours spent on A, and let's say S will be the number of hours spent on food of type B. True, we could even do away with less parameters. We could directly express one of those in terms of the other, because we know that the total amount of time is 10 hours. But let's maybe defer it to when we discuss constraints. Okay, so now we have the function. We know what it should be the function of. Okay, next part will be the constraints. So the constraints is, well, they should answer the, sorry? Yes, the question is not. So the constraints are, well, should answer the following question. If we are given our answer in terms of S is such and such and T is such and such, would we accept such an answer? And the answer is, well, no. Not every S and not every T will be good for us. One obvious constraint here is Akapi spends 10 hours a day looking for food. So the total of T and S is 10. But of course this is also not enough. So what other constraints do we have? So the suggestion was that we should try to derive a constraint from the fact that the nutritional value of B is 3.5 times larger than that of A. Well, I would argue that it's not a constraint. Why do I think it's not a constraint? A constraint is something about, well, it should answer the following question. If you are given some numbers T and S, are they okay for my problem? Well, this is not about T and S. This is about nutritional value of A, nutritional value of B. So it's not a constraint for me. It does not give me an extra information about what numbers S and T will be good for me and what won't be. So first of all, we already exhausted the, well, we already have enough constraints of the equality type. Remember that we have two kinds of constraints, equalities and inequalities. The number of equalities should be one smaller than the number of parameters, if you want to eliminate all parameters but one. So here we have two parameters, and we already found one equality. So at this point we should stop looking for equalities. But once again, not every pair of numbers S and T will be good for us. What should also be true? t bigger than 0, yes. That's obvious. And also s bigger than 0. If you get an answer that involves in a copy looking for food for -5 hours, well, we know it's wrong. So we must have these constraints. Also, well, another obvious constraint which might or might not be necessary, in fact, these constraints are quite enough. You might also notice that there are constraints of the following type. T is smaller than 10, and S is also smaller than 10. You'll see that those are a little bit less important than these two, because they follow from these two and this constraint. But it's always good to have extra constraints than not to have enough. So if you have extra constraints, well, you can make sure that they are all satisfied. Yes, they are not all independent, but that's okay. If you don't have enough, you run into the problem of you might get an answer which is actually not physically possible. Okay, so I don't really see any other constraints in this problem, so we can try to move on. What would be the next step? So we have our function, we have parameters, some constraints. Okay, so first of all, I would say that you should write the function just as a function of parameters. Even before we go to expressing it as a function of one variable, let's express it just somehow in terms of the parameters. So write v as a function of both t and s. In this problem, it might be actually the kind of the most non-standard of all. I mean, the whole problem is not very complicated, but this step might be the least obvious. Okay, so v is the total nutritional value of the whole food that the copy has gathered during the day. Well, first observation is definitely the sum of the nutritional value of A plus the nutritional value of B. That's obvious. So let me write that this is nutritional value of A plus nutritional value of B. So here we are kind of relying on our background knowledge of what nutritional value is, and I mean here we are kind of assuming that consumption of A doesn't change the nutritional value of B, or vice versa. Well, but that's unless given unless it's stated otherwise, it's a reasonable assumption to make. Okay, so the total nutritional value is the nutritional value of A plus the nutritional value of B. Now we'll have to decide what is, say, the nutritional value of A. Well, yes, so we do have some information about this. The nutritional value of A is 3.5 times bigger than the nutritional value of B. Of B is 3, yes. We have some relation between the nutritional values, but, well, somehow we don't know what is the nutritional value of a pound of A. So, first of all, the strategy here would be nutritional value of A is, of course, the nutritional value of just 1 pound of A times the number of pounds. But we don't know what is the nutritional value of 1 pound of A. We know it is some constant. It does not depend on the parameters. It's just the nutritional value of 1 pound of such food, such and such food. Some number of calories per pound. But we don't know what this number is. So we have to introduce some new notation. So let maybe C to denote some constant, which is the the nutritional value of a pound of A. And then we know from here, then the nutritional value of a pound of B is what? 3.5 times C, right. That's just given to us. So once again, we know some relation between these two numbers. We don't know what is the nutritional value of A. Instead, as a number, it actually depends on the units in which you measure the nutritional value. It might be measured in calories per pound, or it can be measured in joules per hour, per pound, or per kilogram, or like. It actually depends on what kind of units you are using. But anyway, it does not depend on our parameters. That's important. The nutritional value of 1 pound of, I don't know, what an akapi eats, maybe grass, does not depend on how much time the akapi spends on eating grass. Okay. So we have this, and now we can try to write B as a function of T and S. B as a function of T and S is as follows. It's the number of pounds. So first of all, the nutritional value of A. Nutritional value of A is the nutritional value of 1 pound of A multiplied by number of pounds of A. Well, number of pounds of A is given to us in the problem. It used to be right here, but it was 4t squared minus t cubed over 3. This is number of pounds of A gathered number of pounds of A, and the akapi gets after T hours. So if an akapi spends T hours looking for A, it was just given to us that it will gather that many pounds of A. And then we must multiply this by the nutritional value of 1 pound of A. Okay, next, it also spends S hours looking for B. So we should take the number of pounds of B that the akapi gets and multiply it by nutritional value of 1 pound of B. So what is the total number of pounds that an akapi gets by spending S hours looking for B? 2 times S. So it spends S hours, and every hour it gets 2 pounds of B. So that's number of pounds of B. And then we must multiply this by the nutritional value of B, which is 3.5 C. So let me write it once again. B of T and S is 4t squared minus t cubed over 3c plus 7sc. Okay, so now we are much closer to something that we know how to solve. Now we have a function of parameters. We want to maximize it. Unfortunately, it's a function of 2 parameters. But it's quite easy to express one of the parameters in terms of the other. So express S as a function of A. Well, it's very easy. S is just 10 minus t from this equation. Well, every time we get rid of one of the parameters, we must convert the constraints we had on this parameter to constraints on the other parameters. So in this step, we must also say the following things. We knew that S must have been positive. It means that 10 minus t must be positive, which means that t must be smaller than 10. And also we know that S should be smaller than 10, which means that 10 minus t should be smaller than 10, which means that t is positive. So actually, well, if you look at the answer, we did not get any new constraints about t. Well, but still, it was important to make sure that we actually did not get any new constraints. And also, if we forgot about one of the constraints about t, well, but did not forget for some reason the constraints on S, we would have found out some of those. Okay. Now we can write b as a function of t alone. I plug in my S, so it's 4t squared minus t cubed over 3 times c plus 7 times S, which is 10 minus t, and times c. And the question is, maximize b of t on the interval from 0 to 10. Now it's a really simple problem. Here's a function, find its maximum on an interval. So we find the derivative. Recall once again that c is not a variable. It does not depend on t. C, well, for us is just a number. And I mean, it is true that C kind of might change depending on season. Nutritional value of grass might be slightly different in summer or in the winter. So what's important here is that C does not depend on T. It does not depend on the parameters that are allowed to change in the problem. So during the day, the C does not really depend on how much time the copy spends looking for A of a week. Okay, so now the derivative relative to t, c is just a constant. The derivative of this is 8t minus t squared plus 7 times minus 1 times c. So it is c, I can take it out of brackets, and I get 8t minus t squared and minus 7. We'll now locate the critical points. First question is there some point where the derivative does not exist? Well, no, v prime of t exists for all t. The next question is when it is 0, and that's 0 when this expression is 0, c times 8t minus t squared minus 7 is equal to 0. The product can be 0 when one of the factors is 0. But c will, I would say, once again, you might make some assumption, but it is a reasonable assumption that c is not 0. C is a nutritional value of 1 pound of some food. Well, we hope that it is not 0. But it does get some energy from eating this. Okay, so this means that 8t minus t squared minus 7 is equal to 0. But we rearrange this as t squared minus 8t plus 7 is equal to 0. Now factor this. So it should be t plus something times t plus something is equal to 0. -1 and -7, yes. So you are looking for two numbers whose sum is equal to 8 and whose product is equal to 7, and it's easy to guess those. It's just 1 and 7. So we get two answers. T is equal to 1 and t is equal to 7. Well, it's a natural thing to kind of be happy that we found the answers, but two things. One, you must check that they satisfy the constraints. That's very important. Even though it's obvious, we must make sure that it's written down. Yes, we did check those. So both t equal to 1 and t equal to 7 satisfy our constraint that t is between 0 and 10. Well, next, we must find the maximum. We found just two critical points. It's not a given that even one of them is maximum, let alone that both of them are maximum. So we have to decide which one might be a maximum or where is the maximum. So what should we do? Okay, so I heard two suggestions. One of them is compute the second derivative, the other one compare the endpoints. Both suggestions will work. So maybe I'll just explain about the endpoints and then we'll do the second derivative. So one of the ways to proceed from here is just compare four values. B at the point 0, B at the point 1, B at the point 7, and B at the point 10. Whichever is the largest, it is our maximum. Another way to proceed is indeed to try to analyze whether these points are local maxima and local minimum, and then try to see what happens to the function. So since my derivative is quite simple, well, I won't spend too much time on computing the second derivative. So I'll do this. The second derivative is c times 8 minus 2t. So the second derivative at point 1 is 6c, which is positive. Once again, we are making some assumption about c, but well, it's just reasonable that nutritional value of something is a positive number. It would be strange to lose energy from eating something. And at the point 7, the second derivative is c times 8 minus 14, so it's minus 6c. It's negative. So what does it tell about the points 1, 1, and 7? Well, t equal to 1 is a local, which one? No, maximum or minimum? Minimum. So my function at this point is concave up, so it is local minimum, and t equal to 7 is the local maximum. Well, unfortunately, this is also not enough. Yes, I know now that t equal to 1 is not what I'm looking for. It's just a minimum. I do know that t equal to 7 is a candidate. The maximum, the absolute maximum might be located at t equal to 7. But let me try to sketch how the function looks like. V of t looks like this. It has a minimum at point 1. It has a maximum, local maximum at point 7. From the minimum to the maximum, well, it must increase because it never changes direction in between. It doesn't have other local minimum maxima. From here, it must decrease. And from here, well, from 0 to 1, it must also decrease. So where is the maximum? Well, here. Or if the function decreases really fast here, it could be also at this left endpoint. So we definitely see that it cannot be at the point 1, it cannot be at the point 10, but it could possibly be at the point 0. We are not sure. Might be or might not be. So you'll still have to compare, but now 2 values, not 4, but just 2. So we should compare v of 0 and v of 7. Well, let's do this. At the point 0, there's maybe here's v, so 0 times c plus 7 times 10 times c, so it's 70c. And v of 7 is 4 times 7 squared minus 7 plus 3 times c plus 7 times 10 minus t. So it's 3 times c. Okay, I want to compare this to 70c. Maybe let me take c out of the brackets. And I also can take 7c out of the brackets. I'm left with 4 times 7 minus 7 squared over 3 plus 3. So 7c times 28 minus 49 minus 3 plus 3. So it's 31 minus 49 over 3. So it's something over 3. 31, 93 minus 49, 44. And I want to compare this number with 70c. Which one is larger? This one or that one? Well, this one, of course, because this number is at least 10. It's larger. So I see that this value v of 7 is larger than this one, so the actual function looks rather than like this, and the actual maximum is 8.7. Well, and finally there is one more place where you can lose 1 point, and that's in the answer. The answer must be about whatever is asked in the question. And if you look at the formulation of the problem, it asks how much time the Akapi should spend on A. So the answer should be an Akapi should spend 7 hours. So if your answer was, for some reason, say s is equal to 3, well, yes, it is true that s must be equal to 3, but it does not answer the question. So that would need to kind of minus 1 point in this case. You must tell what is t, because that's what the question was. So maybe just, yeah. 7 times. Oh.
Right there, right over here. 7 times minus 1. Where's the minus 1?
The minus 1 came from derivative of 10 minus t. So here we have 10 minus t, and we try to find the derivative. Other questions? So the little bit unusual kind of features of this question where, well, you have to think about what is nutritional value in general, and to realize that it's usually expressed in energy per pound. So you should, to find nutritional value of some amount of food, you should multiply the number of pounds times by the nutritional value of pound. And also this introduction of kind of auxiliary constant C, which frankly didn't play any role in all the calculations. We just always took it out of the brackets and then we just canceled it. But still we had to do something. I mean, we can't just ignore it. So maybe any questions about this? Okay, so let's then discuss something shorter, kind of more relax a little bit. If y is f of x is differentiable, x equal to 3 and f prime of 3 is equal to 5, find the limit as x goes to 3 of x squared minus 2x divided by f of 3 minus f of x. Such a question is much more typical of short kind of question that was short question on one of the previous exams. So short doesn't mean that you must immediately see the answer and write down the answer immediately. It just means that the calculation, once you know what kind of calculation to perform, the whole calculation should not take too much space. So let's look at this question. Function is differentiable at the point 3, we are given the value of the derivative. Question is find such a limit. First, you should try to do it in the simplest, most plain way. When x goes to 3, the numerator approaches 3 squared minus 9, 0. The denominator, what happens to the denominator? X approaches 3. Approaches 0, yes. So in general, not every function, not for every kind of function, as x goes to 3, f of x will go to f of 3. Only for continuous functions, as x approaches 3, f of x will approach f of 3. Is our function continuous? So the answer is yes. And the new question is why it is continuous? It's differential. Yes, it's more than continuous. Not only it's continuous, it's differential. It has tangent line, it moves very smoothly around this point. Okay, so now we have a problem. Numerator goes to 0, denominator goes to 0. We have quotient of two small numbers. What should we do next? Well, let me do some first step. One thing that we do always in this situation is try to factor out the things which go to 0. So in this case, it is limit of x minus 3 times x divided by f of 3 minus f of x. As x approaches 3. So at least we know that well, this x is pretty innocent. It just goes to 3 as x goes to 3. The problem comes from this x minus 3 factor. So we kind of isolated the problem. Well, what next? What can we do? Well, maybe try to look for hints in the question itself. Did we use everything that was given to us? Is there something that's given to us which might help?
This entirely is equal to 5.
Okay, yes, so we are given the derivative is 5 at this point. And if you recall what is the derivative, it does look somewhat like this. I mean, it is the limit of some expression is f of x, f of 3, x and 3. So at least should tell you that it may be relevant. So let's recall, this condition is in fact about this thing. Limit as x goes to 3 of f of x minus f of 3 divided by x minus 3 is 5. This is just about f prime of 3 being 5. Okay, now it should be clear what to do next. We see that this expression is actually not that far away from this expression. In fact, you can write this thing, limit as x goes to 3 of x minus 3 times x, f of 3 minus f of x. First of all, as here I have f of x minus f of 3, and here I have f of 3 minus f of x. Well, no problem. I will introduce an extra minus sign and convert this to minus f of x minus f of 3. And also another problem, here I have f of x minus f of 3 on top, and the other guy on bottom, and here it's vice versa. But it's also not really a problem. I can rewrite it as limit as x goes to 3 of x divided by minus f of x minus f of 3 divided by x minus 3. So I move this guy x minus 3 from the bottom of the whole expression to the bottom of just this expression. And algebraically I did nothing, I just rearranged the terms here, but now I see that this expression is exactly this expression. Now I can use this knowledge. So what I get is that this is x goes to 3 and denominator goes to minus 5. So you see that once you know what to compute, what to do, the whole calculation is not that long. That's a feature of short answer questions. It's not that the calculation will not be tricky. It might be tricky, but well, it must be short. Otherwise, it wouldn't be a short question. So if you find yourself doing very long calculations on a short question, try to stop for a second and think. Maybe there is something to employ. Okay, so maybe any questions about this one? Yeah. How to flip? So I use kind of such a thing. A, B over C is the same as B divided by C over A. Oh, so to go from here to saying that limit of this, if you think this is 1/5, is that what you suggest?
So how can like how can
It's just given to you. The derivative of 0.3 is equal to 5.
so it's like from the equation or the after equation how
So once again, this equation is only about the derivative. Next, I did some purely algebraic manipulation to this thing. It's not about limits, not about derivatives, just this expression is the same as this expression. And the same as this expression. Just pure algebra. I just manipulated things, used such a trick. But now I see exactly the same expression here as I see here. And now I know that when x is close to 3, this expression is close to 5. So this expression is close to 5, and this is close to 3. So overall, it's 3 over -5. Other questions? Well, and also, well, do have in mind that you might be tested on definition of derivative, even if the question is not asking compute derivative of such and such function at such point using definition of derivative. Just must know it and kind of have it around during the exam. I mean, once you see such a thing, you must, I mean, something in your mind should scream, there is derivative somewhere. There is f of x, f of 3, x minus 3. It's something about derivative. So I promised somebody here to discuss a business problem. I don't know whom, but well, I will. So the problem is like this. Suppose the demand equation for some product is B, which is 400 minus 50 cubed. And the marginal cost is 800 over 2 plus 5. Determine U that maximizes the product. So it's also a question from one of the past exams. Well, the actual question on the exam was formulated slightly different. It was about some, I don't know, some company that produced such and such products, and the demand equation was such and such. The marginal cost for producing one extra good was such and such. But anyway, that's kind of the skeleton of the problem. What's actually given? What's given is demand equation and marginal cost. And the question is what level of production maximizes the profit. And what's a little bit unusual about this problem is, well, you are not given the actual cost, only the marginal cost. Typically in such a problem you would be given cost, P and Q, but here well, only marginal cost is given. But still, for the solution, we should go through exactly the same steps. We should write down what we are trying to maximize. We should write down what we are trying to maximize, what So express it as a function of just one parameter and find the maximum of this function on some input. So let's do this. We are trying to maximize the profit. What is the profit? Revenue minus the cost, exactly. Well, revenue, I know what it is. It's price times quantity. And cost, well, is cost. Well, I would want to express my function as a function of just one parameter. Here I have some choices. I can try to express everything in terms of P, or express everything in terms of Q. Well, I guess that's the only natural parameters here. Unfortunately, I can't do this explicitly in this problem at all. I'm not given what the cost function is, neither in terms of P nor in terms of Q. But still, I can do parts of this. I'll try to write this as a function of one parameter as much as I can. So I'll leave the cost as it is, but I will write these things as function of one parameter. What parameter to choose? Should I choose P or Q as a parameter? Why Q? Okay, so the reason is, let me give you the wrong reason. The wrong reason is because the marginal cost is expressed as a function of Q. Well, that's the wrong reason. Even if it is expressed as a function of Q, there is no problem to convert this to a function of P. That's not the reason why I will choose Q as a parameter. The real reason is because what is marginal cost? Well, we know it is the derivative of cost. Derivative of cost relative to what? To quantity. It's dc by dq. It's not the derivative of cost relative to price. And I know that at the next step I will try to differentiate my function. So if I want the derivative of cost relative to q to appear, I must express my function as a function of q. So it's really important to use here the q as a parameter, not price. So I'll convert the price into a function of quantity, which is given to me, 400 minus 50q times q and minus c. Okay, now I can find the derivative of profit relative to q, or well, simply put just p prime. So I differentiate this using the product rule. So 400 minus 50q times 1 and plus q multiplied by derivative of this, which is minus 50, and minus, well, derivative of cost relative to quantity, dc by dq. And luckily for us, well, not luckily, we made it so we chose the parameter correctly, so that this derivative is given to us. dc by dq is the marginal cost by definition, and it's 400 over q plus 5. So we can write p prime is 400 minus 100q minus 800 over q plus 5. And now we must maximize the profit. We know the derivative. We find the critical points. Critical points. P prime does not exist. Well, there is a point where it does not exist. When q plus 5 is equal to 0. When denominator here is 0, derivative does not exist. i.e. q is minus 5. So true, it is a critical point, but it shouldn't really worry us. We shouldn't be concerned about this. Why not? It's negative, yes. And Q for us is production level, it must be positive. So this is irrelevant since we want only positive. Okay, let's think that there are other critical points. Well, P prime is equal to 0 when this whole expression is equal to 0, 400 minus 100 q minus 800 over q plus 5 must be equal to 0. We should try to solve this. And let's multiply by this q plus 5 to get rid of denominator. So it will be 400 times q plus 5 minus 100 q times q plus 5 minus 800. And all this is equal to 0. Let's open the brackets. Minus 100 q squared plus 400 q and minus 500 q. So it's minus 100 q plus 2000 minus 800. So it's plus 1200. Let's divide by minus 100. So we'll get q squared plus q minus 12 is equal to 0. It's a quadratic equation. Once again, it's easy to guess what are the roots. It should be q plus something times q plus something. Minus 3 and plus 4. That's correct. So we should find two numbers whose sum is plus 1 and whose product is minus 12. Well, here are the numbers. Q minus 3 times q plus 4. We can check. Minus 3q plus 4q is 1q. Minus 3 times 4 is minus 12. We get two solutions. Q equal to 3 and q equal to negative 4. Once again, one of them should not concern us. This one falls outside of the interesting range, so this is once again irrelevant for the same reason. So we have only one critical point. Well, we'll still have to check whether it's a maximum or a minimum. I mean, yes, it is the only critical point. So if it is a local maximum, say it will be the global maximum. But is it a local maximum? How to decide? Well, let's find the second derivative. The function, once again, is not very complicated. So let's find the second derivative. Minus 100, it will be plus 800 divided by q plus 5 squared, multiplied by derivative of q plus 5, which is 1. So p double prime in the point 3 is minus 100 plus 800 over a squared. It is minus 100 plus 100 over 8. Definitely is negative. So q equal to 3 is the local. Second derivative being negative means functions rotate down. It's local maximum. So p looks like this. In the point 3 it has a local maximum and no other critical points. So whatever it is, it only decreases from its maximum, only gets smaller. Hence, this q equal to 3 is the global maximum. So q equal to 3 is the absolute maximum. Yeah. So if this were a local minimum, then then you'll have to compare the endpoints. Then one of the endpoints is 0. The other endpoint, it's a little bit hard to argue in this case. I mean, you can say that it's kind of infinity. You'll have to compute the limit for what happens to the function at infinity when q becomes really, really large. So you produce lots and lots of items. Do you get more and more profits? In this particular question, the demand equation was 400 minus some number times q. I believe it was like this. And in this particular question, if this turned out to be a local minimum, then what happens when q becomes really, really large? Well, the price will be negative, and then the profit will be negative. So, I mean, you know that the maximum of the profit is not at infinity, so it would be probably at 0. So in this particular business, you are better off not doing this business. But no, it is local maximum, so we are not in this strange situation. And the answer is, the question was, what is q? And the answer is q is equal to c. So, questions about this? So maybe somebody brought some questions home. So let me discuss one more question, which is slightly not typical for a final exam question, or even not at all typical for a final exam question, but still it is a good question. Yeah. So the question was not in this question, but in the previous one with f of x minus f of 3. If you use L'Hopital's rule, would it count? So I would say that. So I believe that yes, it would count. I mean, you would get the points, but only if you explicitly state I am using L'Hopital's rule, and L'Hopital's rule states the following thing. I mean, because we didn't cover this, we can't really rely on whoever is reading it to know that, well, you also know what is L'Hopital's rule. So we have to state what L'Hopital's rule is saying, kind of, if limit of f of x as x goes to a is equal to 0, if limit of g of x as x goes to a is equal to 0, then limit of quotient is limit of the quotient of derivative. Once you state this, well, yes, you can use it. I mean, I'm not sure that it will save you time this way. But, I mean, definitely, if you can't solve the question in any other way, and using this you can solve it, well, it's better. There is a problem with this, because we did not cover this in the course, so we don't know whether you are kind of, I mean, using it for correct reasons or for incorrect reasons. Whether you check the condition that, I mean, there is a room for judgment here. So you will not 100% sure to get the 100% points. Other questions? Okay, so let me try to save a little bit time on wording the problem. I'll give just a diagram. And the length Okay, so the question is as follows. You have a boat somewhere in the sea, you have a dock which is above the sea, and you pull the boat using a rope. And what's given is the rate of change of the length of the rope is constant. So we are pulling it, well, at constant kind of. And the question is, must, or rather does, the speed of the boat increase or decrease if you're doing this? So the question is, you have some machine, or well, you are pulling the rope at a constant rate. So every second you pull, say, 1 meter of rope towards you. And this, of course, makes the boat come closer to the dock. And the question is, well, what happens to the speed of this boat? Will it always increase? Will it always decrease? Or maybe it will increase and decrease? Or maybe stay constant all the time? What's going to happen? So maybe before we actually solve the question, maybe let's see what are your predictions. Will it always increase? Just raise your hands if you think that it will increase. Okay, will it always decrease? Okay, so it seems that we are more inclined to think that it will decrease. Okay, let's try to solve this. It is, of course, a related rates problem. You are given information about one rate of change, which is the rate of change of length of rope. And the question is, what happens to another rate of change, which is the speed, it's the rate of change of the distance, this distance. Well, let's give some names to the quantities which are changing. This is L, the length of rope. And another one is X, the distance from the boat to the dock. Well, they are given that dl by dt is constant. That's given. We are pulling the rope, well, at a constant rate. Say 1 meter per second, something like this. Question: what happens to dx by dt? Does it increase or decrease? And to be honest, it's not even about dx by dt. Dx by dt is just the velocity. It could be positive or negative. In this case, it will be actually negative because x decreases with time. As time goes by, the boat gets closer to the dock, so x decreases. So the question is, what happens to the absolute value of this? Does it increase or decrease? Does the speed increase or decrease? Well, we must find some relation between the rates of change. For this, we must find some relation between the actual quantities, between x and L. And it's reasonable that if you know what is the length of this rope, you should be able to find out what is this distance. So what is the relation between the two? How can we write down the relation? Say again? Right angle triangle, yes. So we can use Pythagoras theorem. We know that this squared is this squared plus that squared. And we also know that this distance, whatever it is, well, let's call it h, is not changing. The dock does not go underwater or doesn't fly to the sky. So whatever it is, we have x squared plus h squared is equal to L squared, and h is the constant. That's quite important for us. Yes, it is true that we are not given what it is, we do not know what is h, but still it is not changing. Then we can try to differentiate this. We have a relation between x and L. Let's find a relation between rates of change. So differentiate. We get 2x dx dt plus, what is the derivative of h squared? 0, because it's not changing, is equal to L, 2 times L times dl by dt. So dx by dt is L over x times dl by dt. Well, we are interested in absolute values, so let's write dx by dt in absolute value. Well, both L and x are positive, so applying absolute value doesn't change this. dl by dt is in fact negative. The length of rope decreases, so we should put an absolute value sign on this as well. Well, so we have a relation between rates of change, dl by dt and dx by dt. We know that this part is constant. Does not change. That's being pulled, and the length of the rope is decreasing at a constant rate. So the actual question is, what happens to this L over x? Does it increase or decrease? Okay, so some range of opinions here. So I heard increase, decrease, and stay constant. So let's look at this. As time goes by, well, definitely L decreases, but also x decreases. So whether the quotient increases or decreases actually depends on, well, kind of how fast one of them decreases relative to the other. So it might be not that obvious what happens to the quotient. But here geometry might help you. Look at this picture. What is L over x? Is it related to some growth? Okay, very good. So you have this angle, let's call it alpha. Cosine of alpha is in fact x over L. It's this distance over that distance. So L over x is 1 over cosine of alpha. Now what happens as time goes by? As time goes by, what happens to alpha? Does it increase or decrease? Increase. Now it's obvious. The ball gets closer, the angle becomes larger. Alpha increases. What happens to cosine of alpha? Well, let's imagine how cosine looks like. It looks like this. And we're interested in alpha between 0 and pi by 2, only all the way up to it, until it hits the dot. So definitely cosine of alpha decreases. So 1 over cosine of alpha, well, increases. So dx by dt, which is 1 over cosine of alpha times dl by dt, also increases. Yeah.
What is the absolute value of dx?
So first of all, dx by dt is just velocity, and absolute value I put it because I'm interested in speed.
Oh,
in this particular case, x is decreasing, so the velocity will be negative, but well, I'm interested in negative. Just absolute value. Okay, so thanks everyone for coming to most all of the lectures, and have the best luck.